Welcome to Lecture 4 of How to Read and Do Proofs. Now that you know the forward-backward method, what we're going to do in the remaining lectures is learn new proof techniques. And all of these new proof techniques are what I call keyword-based proof techniques. So let me explain what I mean. Imagine that you learn these dozen or so proof techniques, and now you are faced with trying to prove a new proposition, A implies B. How do you know which of these dozen proof techniques you should use to start this proof? It turns out that often there are certain keywords in the statements A and B that will tell you which proof technique is likely to be a successful one. In other words, every technique that I'm about to teach you now has certain keywords associated with them. And when you see those keywords, that's when you should think about using the associated proof technique. Keywords can appear in either the hypothesis A, or somewhere in the forward process, or in the conclusion B, or somewhere in the backward process. And correspondingly, for a given set of keywords, there are two different proof techniques. One that is likely to be used if you encounter those keywords in the forward process, and one proof technique that's likely to be used for those keywords in the backward process. So this is why it's very important for you to be very clear whether you are in the forward process or whether you're working in the backward process. So let's take a look at some keywords. There are two special groups of keywords that collectively are called quantifiers. So one group of keywords is the existential quantifier, there is, there are, there exists. The other group of keywords are referred to as the universal quantifier, consisting of the keywords for all, for each, for any, for every. These keywords appear in virtually all branches of mathematics, and so what we're going to do is start with the existential quantifier. There is, there are, there exists. Let me illustrate the use of the existential quantifier with the definition of a rational number. A rational number is essentially a fraction, and to write that formally, here is a definition. A real number is rational if and only if there are integers p and q with q not equal to 0, such that r can be written as the fraction p divided by q. That's a rational number. It's a fraction, p over q. And if you look at this definition, right here you will see the keywords there are. Okay, now when you write statements, you always want to be conscious of whether you should include quantifiers. So for example, if you know that r is a rational number, you might write something like this, r equals p over q. And if you were to write it this way, there would be a problem, because when you write r equals p over q, the symbols p and q are undefined. What are they? You may know what they are, but you haven't written them down. This is what I call a syntax error. A syntax error is when you have symbols that are undefined, or, for example, an operation that cannot be performed. This is incorrect. If you know that r is a rational number, then here is what you should write. There are integers p and q with q not equal to 0 such that r equals p over q. You need to put in the quantifier and you need to describe your symbols, integers p and q. Okay, the quantifier there is allows for the possibility of more than one of these objects. Let me give you an example with the following definition. An integer n is square if and only if there is an integer k for which n is equal to k squared. So for example, n equals 9 is a square because n can be written as 3 squared or minus 3 squared. So there are two possible values for the integer k when n is 9. If you look at these kinds of statements that contain existential quantifiers, what you'll begin to realize is that they can always be written in a standard form. And that standard form looks like this. There is an object with a certain property such that something happens. Now your job is to learn to read these kinds of sentences and identify the object, the certain property, and the something that happens. So I'm going to denote that by O, CP, and SH. The object, the certain property, and the something that happens. Let's take some examples and see if you can identify the objects, the certain property, and the something that happens. There is an integer x greater than 2 such that x squared minus 5x plus 6 equals 0. Okay, what is the object here?
An integer.
Which integer? Integer
X.
x, right. The integer x is the object. What is the certain property? Being greater than 2. And what's the something that happens? X squared minus 5x plus 6 equals 0. Everybody okay with this example? Okay. When you identify the object, be sure to specify what kind of object you have, what type of object. You can do that with words like integer x or function f, or you can describe the type of object by saying it belongs to a certain set. Let me show you why it's important that you identify the type of object. Let's take a look at this example. There is a number x greater than 0 such that x squared equals 2. Is that statement true or false? If we're talking about a real number, then you are correct. The statement is true. What if we're talking about an integer? Is the statement true? No. So if x has to be an integer, then the statement is false. And so what I'm trying to point out with this example is that when you talk about a number x, that's not enough. You need to be very clear on what kind of object you're talking about. Because in this example, if you're talking about a real number x, then that makes the statement true. Whereas if you're talking about an integer x, that makes the statement false. So the message here is that when you talk about an object, be sure to include the type of object. Another comment is that sometimes the type of object is implied from the context. Let me give you an example. There is an n greater than 1 such that n factorial is greater than 2 to the n. What is the object here?
An n.
An n, but that's not a good enough description. You need to include the type of object. What type of object is n in this case in order for this statement to make sense?
An integer.
An integer, that's correct. If n were a real number, n factorial wouldn't make any sense. So what I'm trying to tell you here in this example is that the type of object can often be implied. It doesn't say anywhere in here that n is an integer, but in order for n factorial to make sense, n has to be an integer. The certain property is being greater than 1, and what's the something that happens?
N factorial is greater than 2 to the n.
N factorial is greater than 2 to the n. Mathematicians have developed a lot of symbols for shorthand notation. And in particular, for the existential quantifier there is, they often will use the symbol a backward E, capital E, and this symbol here for the words such that. For instance, they might write, there is an angle T such that cosine of T equals T. All right, so please help me. What is the object here? An angle T, which is really what kind of an object? A real number. What's the certain property?
There isn't one.
There isn't one, exactly. That is possible. There is no certain property, and what's the something that happens?
Cosine of t is equal to t?
Cosine of t is equal to t. So it is indeed possible that there is no certain property. In summary, when you see the quantifier there is, you should see it in the following standard form. There is an object with a certain property such that something happens. And what you need to be comfortable at is identifying the object and its type, the certain property, and the something that happens. Keeping in mind that the type of object could be implied from the context in which it's used. It may not explicitly say integer n. And the certain property may in fact be omitted. Any questions on standard form? Okay. Now let's talk about proof techniques. These key words, there is, there are, there exists, can appear in either the forward process or the backward process. And consequently, there are two essentially separate proof techniques. let's talk about the keywords there is appearing in the forward process. Let's suppose your statement A looks like this. There is an object with a certain property such that something happens. Now, because this is a forward statement, you know that that is true. You know that there is an object with a certain property such that something happens. Let's call that object X. Because you know that there is an object X with a certain property and the something that happens, you can simply use that object to create a new forward statement. There is really nothing special that has to be done. You simply use the object with its certain property and the something that happens to work forward and create a new statement. And because it's so straightforward, I'm not going to give it a separate proof technique name. So when you see the keywords there is in the forward process, you simply use the object with its certain property and the something that happens. That's all there is to the keywords there is in the forward process. The more interesting situation is when you see the keywords in the backward process. So let's take this example here. Suppose your conclusion is there is an object with a certain property such that something happens. Now, because this is in the backward process, it's your job to show that there is an object with a certain property such that something happens. Now, the question is, how are you going to show that there is such an object? And there are different ways to do this, but one of the most common ways is what I'm going to call the construction method. With the construction method, the idea is to go out and actually produce this object. How do you produce it? Well, you guess it. You use an algorithm to produce it. You create it somehow. I can't tell you exactly how to produce the object. This is an art. Doing proofs is an art, not a science. But what I can tell you is when you see the keywords there is in the backward process, think about using the construction method, which means you have to go out and construct this object. One thing I can tell you is that typically, in order to construct the object, you want to use the information in the hypothesis A. In fact, when I see the keywords there is in the backward process, I say to myself, I need to construct this object. How am I going to do that? I typically turn to the forward process and I work forward from A to use that information to construct this object. The second comment I want to make is that constructing the object in itself does not constitute the proof. After you construct the object, it's your responsibility to show that it is the correct object. What do I mean by the correct object? The object you constructed has to satisfy the certain property and the something that happens, and it's your job to show that. Let's take an example and see how this works. Here's a proposition. If A, B, C, D, E, and F are real numbers for which AD minus BC is not 0, then you can solve the equations AX plus BY equals E and CX plus DY equals F for the real numbers X and Y. Here's the hypothesis A and the conclusion B. Okay, the second thing you need to do is choose a proof technique. Now, what I urge you to start thinking about as we go along is looking for keywords, such as?
There is.
There is, right? There is, there are, there exists. That's the only one we know. We're going to learn others. But right now, let's look for the keywords there is. Do you see that anywhere? No. Okay, good. So start by choosing a proof technique. That is correct, after you identify the hypothesis A and the conclusion B. And then look for keywords and see if you can find them. And in this particular case, you do not explicitly see the keywords there is. However, what does it mean to say you can solve the equations AX plus BY equals E and CX plus DY equals F for the real numbers X and Y? What does that mean?
There is a solution.
There is a solution. See the keywords? There is. There is a solution. So this conclusion, you can solve the equations AX plus BY equals E and CX plus DY equals F for the real numbers X and Y. You can rewrite B in this form. There are real numbers X and Y such that AX plus BY equals E and CX plus DY equals F. And when you write it in this form, Now I hope you see the keywords there is in the backward process. So something you have to learn to do is be careful of what I call hidden quantifiers, hidden keywords. They're actually there when you said you can solve. What that really means is there are real numbers x and y for which you can solve the two equations. Now that we see the keywords there is in the backward process, now what proof technique should we use?
The construction method.
The construction method. And in order to use the construction method, first you need to identify the objects, the certain property, and the something that happens. So what are the objects here? Real numbers x and y. Those are the objects. When you describe the objects, include the type. What's the certain property?
There is none?
There is none. And what's the something that happens?
ax plus by equals c and dx plus ey equals f.
ax plus by equals e and cx plus dy equals f. So I have to construct real numbers x and y. Ready? Here they are. You should have a couple of questions. What information in the hypothesis A have I used to construct these values?
A times D minus B times C is not 0.
AD minus BC is not 0. That's where I used the information in A so that I could divide by something that is not 0. What questions do you have?
How did you get DE minus BF?
How did I come up with these values? I'm going to address that in just a moment. You should have another question. How do you know that these are the correct values? I haven't talked about that. So again, let me summarize. With the construction method, you have to go and construct the objects, in this case real numbers, and you have to show that they are the correct ones, that they satisfy the certain property and the something that happens. Now, let me just mention, with regard to question 1, where do these values come from? As the author of a proof, it is not my responsibility to tell you that. Now, it would be nice if I did, and I will do that today so that you can see where they came from. But I urge you to keep in mind, as far as the proof technique of the construction method goes, it's not my responsibility to tell you how I created them. All I have to do is create them and show you that they're the right ones, that they satisfy the certain property and the something that happens. However, when you use the construction method and you write a proof, I urge you to explain for the reader's benefit how you constructed these objects. And I'm going to do that for you right now. Many times when you read a condensed proof, an author will just construct these values and it looks like magic. So let me show you where these two values for x and y come from. Okay. It's very often the case in the construction method, when you have to construct an object with a certain property and for which the something happens, it's very often the case that what you want to do is look at the certain property and the something that happens and sort of play with those properties to try and construct the object. So let me do that in this case. I need the two real numbers x and y to satisfy ax plus by equals e and cx plus dy equals f. True? Okay, so what I'm going to do is I'm going to play with these two equations to see if I can construct x and y. And by play with, here's what I mean. Let's multiply the top equation through by d and the bottom equation through by minus b. And what does that do for me? Well, if you look at d times this equation, look at the d times by and the minus b times dy. What's going to happen when you add these two? D times by minus b dy. 0. They're going to cancel. And what I'm going to be left with, look here, just a little bit of algebra, AD minus BC times x equals DE minus BF. So this is algebra. And now I only have one equation in the unknown x, and this I can solve. And this is where I use the hypothesis that AD minus BC is not 0. So this is how I constructed the value of x. And I'm not going to show you the construction of y, but it's very similar. I'll let you go home and try and play with the two equations and solve for y. two things I need to point out. First, that I did use the hypothesis A to construct the objects. And second, I'm not finished yet. Even with all of this nice explanation, I am not technically finished with the construction method. Yes, I have constructed the objects, but what else do I have to show you? I still have to show you, even with all this added explanation, it is still my responsibility to show you that for these values of x and y that I constructed, they satisfy ax plus by equals e and cx plus dy equals f. So let's do that. Let's look at ax plus by. Let's put in this value of x down here and this value of y down there. Let's put them in, and now this is algebra. They have the same denominator. Let's multiply the a through and the b through. This cancels with this, and if you just clean this up, sure enough, you get e. And I'll let you go home and see that cx plus dy equals f for those values of x and y. So let me take a moment to summarize the construction method. First of all, when should you use it? You should use the construction method when, in the backward process, you need to show that there is an object with a certain property such that something happens. That's the time that you want to think about using the construction method. And the first step in using the construction method is to identify the objects, the certain property, and the something that happens. Then say to yourself, I need to construct these objects. How do you do that? Well, it is an art, so I can't give you fixed rules. But I can give you two very useful guidelines. First, turn to the forward process. Use the information in A to construct the objects. And second, look at the properties you want the objects to satisfy and play with them to see if you can create objects that satisfy those properties. But that's an art. This is not something, unfortunately, I can give you rules for. In any case, after you construct the objects, it is your responsibility to show that they are the right ones. What do I mean by the right ones?
Show that it satisfies the right properties.
That it satisfies the certain property and the something that happens. That is your responsibility. Everybody okay with the construction method? Keep in mind it's in the backward process. Okay. Now, this brings us to a new point in our lecture series. One goal of this series of lectures is to teach you how to do proofs. And that's what we're learning these proof techniques for. But a second goal of these lectures is to give you an understanding of how to read a proof. So what I want to do for the rest of the lecture today is show you a typically written proof and help you learn to read it and understand it. Let's take an example. First, our definition of an even integer. An integer n is even if there is an integer k such that n equals 2k. That's the definition of an even integer. And we have the definition of an integer n divides an integer m, written n divides m, if and only if there is an integer k for which m is equal to k times n. So here are two definitions. We're going to use that in the following proof. If m is less than n are consecutive integers and m is even, then 4 divides m squared plus n squared minus 1. Okay, so of course, the first thing you did was identify the hypothesis A and the conclusion B. And now what I'm going to show you is a condensed proof. A condensed proof in which I have written each sentence on a separate line so that you can read it very clearly. And what we're going to try to do is understand what these sentences mean. So first of all, I'd like you to take a couple of minutes to read through this condensed proof on your own. Okay, now our goal is to try and understand this condensed proof in the context of proof techniques. For example, if you look at this condensed proof, do you see any mention of what we have been discussing here? Do you see a mention of the forward-backward method? Do you see a mention of the key question and the key answer? No. Do you see anything about the construction method? No. Yet all of these things are used in this proof. So our goal is to try to understand a condensed proof as you see it here written in paragraph form, and to understand it as a sequence of applications of the proof techniques, because that's what they are. And your job is to try to figure out which technique the author is using, why the author is using that technique, is the author using that technique correctly, and in many cases, filling in details because the author is skipping steps. So let's do this together, and we're going to practice this in almost every lecture that we do. So again, first let's identify the hypothesis A and the conclusion B. We can assume A is true. Our job is to show that B is true. Now let's look at what the author has written in the first sentence. Let n equal m plus 1. Who can tell me, in the context of proof techniques, where that statement comes from? If you're not sure what proof technique the author is using, look at the statement A implies B and ask yourself, what proof technique would you use to begin this proof? As I mentioned, all the proof techniques we're going to learn from now on are keyword-based techniques. The exception is the forward-backward method. When you do not see keywords, that's the time to use the forward-backward method. In terms of the proof techniques, where does the statement let n equal m plus 1 come from? From the hypothesis, and therefore, in terms of proof techniques, the author is working
Forward?
forward, exactly. The author is working forward from the hypothesis that m and n are consecutive integers. Okay, so now the author says, then m squared plus n squared minus 1 is equal to m squared plus m plus 1 squared minus 1, which is equal to 2m times m plus 1. Let's see if we can understand where this is coming from. M squared plus n squared minus 1 is equal to, let's first put in n equals m plus 1, and now let's expand m plus 1 squared. M squared plus 2m plus 1. What happens to the plus 1 and the minus 1? Cancels. And what have you got left? 2m squared plus 2m, and if you factor out 2m, you get 2m times m plus 1. We have to fill in the missing details. Does everybody remember that analogy that I gave in lecture 1 of the chessboard, where I said, here's the chessboard, and then I showed you 4 moves later what the chessboard looks like? That's exactly what's happened here. Here's the chessboard, and here it is 4 moves later. You have to fill in the details of the missing steps. To understand why the author is doing this particular algebra, we need to work backward from here. And let's do that, you and I. The key question here is, how can I show that an integer divides another integer? One way to answer that is by definition, and here is the definition in which I have avoided overlapping notation. So please look at how I've used A, B, and K so that I don't overlap with M and N. Okay, so let's go back to the key question. How can I show that an integer divides another integer? We need to match up notation here. Match A to who? 4, and B to m squared plus n squared minus 1. And now the answer is I have to show that there is an integer, say p, such that m squared plus n squared minus 1 equals 4p. So let's look at B1. If B1 is true, then B is true. So now I can focus my attention on B1. And if you look at B1, what do you notice?
There is.
The key words there is. I have to show that there is an integer, say p, such that m squared plus n squared minus 1 equals 4p. And if this is what you have to show, what proof technique should you be using now?
The construction method.
this is where you should use the construction method. And let me tell you something, that's exactly what the author has done. But the author has not said that. The author has not said, excuse me, reader, I'm about to use the construction method. However, I guarantee the author has used the construction method. So let's try that ourselves just to get an understanding here. What is the object?
Integer p.
An integer p. What's the certain property?
There is none.
There is none. And what's the something that happens? M squared plus n squared minus 1 equals 4p. So the author should be now constructing a value for p. Recognizing the keywords there is in B1, you and the author should now use the construction method to produce the value of the integer p. Now, a good exercise is to go back to the proof and read it, the condensed proof, and see if you can identify what p is. The author has to construct an integer p for which m squared plus n squared minus 1 is equal to 4 times p. Can somebody identify from what is written here what the integer p is?
K times m plus 1.
K times m plus 1, right here. In the statement S4, there is the integer p, 4 times p. We still don't know what k is, but that's exactly 4 times p. Now the author writes in sentence 3, because m is even, there is an integer k such that m equals 2k. This is nothing more than working forward from the hypothesis that m is even by definition. And here you see the keywords there is in the forward process. Now, if you recall from the lecture, when you see the keywords there is in the forward process, you can simply use the object. What we hope to do here is use this integer k to construct this integer p. That's what we hope to do. And how do we do that? Well, let's see what the author does. So here's where we are, and now let's read S4. It now follows that m squared plus n squared minus 1 equals 2m times m plus 1 equals 4k times m plus 1. And so 4 divides n squared plus m squared minus 1. So the question is, where is the value of p? Can you see it here? K times m plus 1. Just the k times m plus 1. The 4 matches up, so I just make p equal to k times m plus 1. So what the author has done here is use some algebra. M squared plus n squared, let's do it together. M squared plus n squared minus 1 is equal to 2m times m plus 1. Where did that come from? A2. And now the author does this. M is equal to 2k, so put in 2k right there, and what do you get? 4k times m plus 1. And now you can see what the construction of p is. K times m plus 1. There's the construction method. The author just didn't say it. Not only does the author not mention that that's the construction, but remember how the construction method works. You have to construct the object, but then what do you have to do? Show that it's the right one, right? You have to show that for this value of p right here, for this value of p, m squared plus n squared minus 1 is equal to 4p. And that's essentially what the author has done here. But what we really need to do is put in this value of p right here and show that m squared plus n squared minus 1 is equal to 4p. The author just leaves that for you to check. And that, my friends, is an explanation of this proof in the context of proof techniques. So let me summarize some of the issues associated with reading proofs. First, one of the reasons that reading these condensed proofs is challenging is because the author doesn't mention proof techniques by name. Did you see anywhere in the written proof the forward-backward method? No. Did you see any mention of the key question? No. Did you see any mention of the construction method? No. And yet the author is using all of that. All of that is going up in here, and unfortunately it's not explicitly written in the condensed proof. So what you need to do to understand these condensed proofs is you always need to ask, what technique is the author using and why? Is the author using that technique correctly? And than filling in details that are skipped. This is typical of reading condensed proofs. Any questions on this example? Okay, let me summarize the construction method. First of all, when do you use the construction method? Use the construction method when you want to show that there is an object with a certain property such that something happens. When you see the keywords "there is" in the backward process, that should be the trigger to think about using the construction method. How do you use the construction method? First, identify the object and its type, the certain property, and the something that happens. Then say to yourself, I need to produce one of these objects. That's the construction method. Go out and construct the object. How do you do that? Well, it is an art, but what I can suggest that you do is turn to the forward process, use the information in A to help you construct the object, and or look at the properties that you want the object to satisfy and play with those properties to see if you can construct the object. That's what we did when we solved those two systems of equations, that system of two equations and two unknowns. And finally, please remember, after you construct the object, you're not finished. Why not? What else do you have to do?
Show that it's the correct object?
Show that it's the right object, that it satisfies the certain property and the something that happens. And then write up the proof in paragraph form so that nobody else can understand it. Any questions on the construction method? Okay, what we'll do next time is look at the keywords for all, the universal quantifier. That completes this lecture.